Have you ever wanted to stump a friend or a math teacher, perhaps to win a bet or get some extra credit? Whatever it may be, I've got two proofs today that should stump just about anybody, and if for some reason they don't, I'll be teaching you how to make your own.
Welcome to Problem Solved.
For the first impossible proof, we're going to show that 2 actually equals 1. And like any proof, we have to start off with a given statement. So the first statement we have here is that x equals 2. That's just the value that we've been given for this proof. For the next step, we're going to multiply both sides by this quantity x minus 1. From there, we're just going to do some distribution. So this x times this x makes for x squared. X times -1 is negative x. 2 times x is 2x, and 2 times -1 is negative 2. From there, we're just going to move some terms around. So this negative x is going to come over here for this positive x. This 2x we're going to subtract over to make for negative 2x on this side. And since both of these terms have an x in them, we're going to just factor that x out, which leaves x minus 2 on both sides of the equation. We're then going to just divide both sides by this x minus 2 term to get that x equals 1. And since 2 equals x and x equals 1, that means that 2 does in fact equal 1. The second proof is going to show that 3 equals 0. And I'm going to start off this proof with a quadratic equation. We're going to set it equal to 0 to solve it. We're going to go about it a slightly different way. We're going to divide everything by x. So x squared divided by x is x. X divided by x is 1, and 1 divided by x is 1 divided by x. And 0 divided by x is still 0. Now, if you're wondering why I've put these parentheses here, well, that's just a grouping, because in the next step we're going to solve for this value x plus 1. If we subtract this x squared over to the other side, we then get that this value, or this quantity x plus 1 is the same as negative x squared. Just going to plug that right back in here. From there, if we add this to the other side and multiply by x, we can get all of our x's on the same side. A cube root then will give us our solution that 1 equals x. And we take that value, plug it back into our original equation to get this plug-in value, which simplifies down to that 3 equals 0. So, by now, you're probably wondering, how does all this work? I mean, obviously 2 doesn't equal 1 and 3 doesn't equal 0, but the math seems correct in both cases. Well, let's take a closer look. So for this one, I mean, the math here all looks fine, the steps are executed correctly, but if we look really carefully at this given statement and what it means later on in the problem, if we look at this compared to this last step, if we said that x equals 2, then the quantity x minus 2 is actually equal to 0. So if we are dividing both sides by x minus 2, and x minus 2 is 0, then we're actually dividing by 0 in this step from here to here. And since we can't divide by 0, we can't trust anything that comes after that step. And so the reason you didn't see that divide by 0 to begin with is because we disguised it as this term x minus 2. And that's an important thing to keep in mind for later in the video when I begin talking about how to create your own impossible proofs. This one has a couple problems with it, and the first is with this given statement. So I said that we're going to solve this quadratic equation, and solving an equation is just looking for where it crosses the x-axis. So if we look at a graph of it, we'll be surprised to see that it doesn't actually cross the x-axis anywhere. And so therefore it doesn't ever equal 0. And so that means that this first statement as a whole is just false. And if our given statement isn't true, then nothing that we've derived based on the given statement can be true either. But there's still another question that remains to be answered with this. I mean, if this equation doesn't have any real solutions to begin with, how do we get an actual real solution for x down here? And the answer comes from a fancily named thing called the fundamental theorem of algebra. And what this really means is just that whatever this biggest power is, that's how many solutions the equation has. The solutions can be complex numbers. Like, for example, if we take this equation and plug it into the quadratic formula, we get our two solutions, but they are imaginary numbers. But if we look closely at this transition right here, we take a linear thing, so this highest power of 1, and change it to a highest power of 2. So by the fundamental theorem of algebra, by doing this substitution, we've actually added a new solution to the equation. That's why we have an x cubed here when we only started with an x squared. So that's something to be careful about, just making sure that you don't have a higher power somewhere in your proof than you did earlier on. Otherwise, you can get a solution that wasn't even part of the thing to begin with. And so with that said, here's the thing that you've been wanting to know. How do people even come up with these kinds of proofs? Well, there's an easy way and a hard way. The easy way for you is just to take the proofs that I've just shown you and change them to look different. So like if you take this 2 and this 1 and replace it with different numbers, say 3 and 7, you could show that 3 equals 7 just by following the exact same steps. The other easy way to do this for this other equation is if you change this coefficient, notice the coefficient is all the same number. If you change that to some other coefficient like 23 or even pi, that will still reduce down to show that 3 equals 0, but it can look a lot more complex, and it can be fun to use pi to show that 3 equals 0. The hard way is the way that these kinds of proofs developed in the first place, and they all come from looking at different conditions or rules that certain math concepts have. So, for example, let's look at this property of square roots. We have that if you have two numbers being multiplied inside of a square root, it's the same as having the first one times the second one as separate square roots. Same thing with addition. But notice this condition that comes along with the property. In other words, this condition is saying that this property, that this equal sign, is only valid if x and y are greater than 0. Which makes sense. If you have a negative number inside the radical, then you can have imaginary numbers. But the trick then is, what if you were able to find a way to get a negative number here under the square root, but without people realizing that it's a negative number? And that's kind of how the rest of this kinds of thing comes together. How can you break this condition, or how can you violate this condition in disguise so that people don't realize that you're violating the condition? There's actually another fun impossible proof that shows that 1 equals negative 1 that abuses this very property in the way that I just mentioned. But I'll let you see if you can figure that one out. So, with all that said, I just want to thank you for sticking around to the end of this video. I hope you enjoyed it. I really enjoy these kinds of impossible proofs. In fact, I'd love to hear from you. What's your favorite impossible proof? Go ahead and leave a comment with that. And if you want to hear more about this stuff in the future, go ahead and subscribe. I'll be uploading more videos with these fun brain teasers. And I think that's really all I have to say for this video. So again, thanks for watching. This has been Problem Solved. Over and out.